Welcome to the presentation on InfinityVM Lightpaper. Today, we'll discuss how InfinityVM aims to enhance blockchain capabilities by focusing on off-chain compute, thus addressing some of the limitations of current blockchain systems. Blockchains were initially designed to facilitate trustless exchanges. They ensure transaction immutability, censorship resistance, and credible verifiability, preventing double-spend issues and eliminating the need for a central authority. Current blockchain design constraints such as execution limits, storage costs, complexity restrictions, and on-chain lag hinder their scalability and flexibility. These limitations make it challenging for applications to perform optimally, requiring a redesign of core blockchain paradigms. Recent advancements have focused on improving performance and expressivity of blockchains. Techniques like alt-VMs and coprocessors, as well as roll-ups, have been introduced to address these limitations, but they come with their own sets of trade-offs, particularly in terms of complexity and cost. By rethinking the blockchain design to focus on decentralized verification with centralized proving, we can achieve high performance, scalability on demand, and ultimate developer freedom, paving the way for more efficient and flexible blockchain applications. InfinityVM integrates off-chain compute with blockchain scaffolding, allowing applications to leverage the decentralized properties of blockchains while maintaining the flexibility and scalability of off-chain resources. This approach ensures high performance, safety, and composability. Off-chain compute introduces challenges like reversion logic and fraud risks. Systems like zkVMs and optimistic techniques can address these issues, but require careful implementation to ensure consistency and security across applications. Enshrining off-chain compute into the protocol is a key solution proposed by InfinityVM to address the challenges of integrating off-chain computations. This approach embeds the computation directly into the fork choice rule of the chain, ensuring that the canonical view of the chain includes honest execution of any off-chain compute. This is achieved by utilizing ZK fraud proofs and tying honest execution of coprocessing into the definition of the valid chain. The result is a system where the canonical state of the chain is guaranteed to include verifiable and honest execution. The diagram illustrates how codependent optimistic coprocessor apps introduce systemic complexity. In Block 1, the coprocessor sends results to App 1, and other apps may derive state from App 1. In Block 2, a coprocessor sends a malicious result to App 1, which leads other apps to read this malicious state. By Block 3, App 1 runs logic to revert the state to fix the malicious result, but other apps have already consumed the malicious result and need separate logic to revert their state. This table compares various off-chain compute integration techniques, highlighting their trade-offs in protocol finality, latency, cost, and developer experience, DevX. Optimistic methods have high finality but place the burden on developers for handling reorgs. ZK methods offer great DevX with no trust assumptions but have high latency and cost. Enshrined OPZK balances these factors with low latency and cost, and good DevX by abstracting the reversion logic. The diagram explains how enshrined coprocessing works. Blocks containing invalid results are invalidated, and forks including them are abandoned. This ensures all applications progress together or reorg together, enabling near-instant composability. This mechanism liberates developers from handling complex application-level reorgs, allowing them to focus on off-chain actions. InfinityVM's approach emphasizes using optimized off-chain servers to run applications and settle state to the base layer of the InfinityVM. Optimizing for the happy path involves a trade-off where proposers are assumed to be honest, reducing prover overhead and costs. This method uses optimistic verification, which assumes successful outcomes and requires a proof only in the case of fraud. Such a system benefits from lower latency and cost while maintaining the integrity of the chain through a robust challenge network that can generate proofs in the edge cases as needed. The InfinityVM sidecar provides a mechanism for developers to request jobs that can run on given sets of inputs and post results on-chain. This includes both on-chain and off-chain data, fundamentally consisting of optimized code running on a regular server to either define or supplement an application. This architecture offers two primary flavors: on-chain apps using off-chain compute, and off-chain apps that post verified state commitments on-chain. This design preserves liquidity on the base layer, avoiding fragmentation and enhancing overall scalability and interoperability. This image depicts two alternative designs for applications: on-chain apps and off-chain apps. The on-chain design uses the InfinityVM to handle app contracts directly with users making calls to these contracts. The off-chain design involves an app server that batches user interactions and communicates with the coprocessor. Both designs leverage the coprocessor for complex computations, illustrating different approaches to where the bulk of computation is processed. The system architecture involves developers submitting programs to the coprocessor network. This network processes asynchronous and synchronous requests, sending the results back to app contracts. Validators ensure the correctness of results while proposers post results on-chain. This setup provides a robust mechanism for handling off-chain computation securely and efficiently. Coprocessing jobs follow a specific process to reach finality on-chain. The challenge period allows for verification of results. If no fraud proof is submitted during this period, the result is finalized. This mechanism ensures that all off-chain computations are correct and verifiable, providing a secure way to handle complex computations. Validity proofs are crucial for finalizing coprocessing jobs on-chain. Provers submit these proofs to demonstrate the correctness of results. Once a validity proof is supplied, the challenge period ends early, finalizing the job. This process ensures that all computations are verified and trusted within the ecosystem. If fraud is posted on-chain by a malicious proposer and successfully challenged, a reversion occurs. The specifics depend on the architecture of the chain running InfinityVM. In a fully independent L1 or sovereign L2, the canonical chain is determined by an honest majority of nodes validating blocks. For InfinityVM as an L2, the protocol must handle reversions by following the base layer's canonical chain. Reversions can be painful, but are necessary to prevent fraudulent state transitions. InfinityVM's deterministic execution engine ensures that the chain remains consistent for honest actors. A central limit order book, CLOB, runs on an optimized off-chain server and uses InfinityVM as part of its blockchain scaffolding. This approach flips the existing smart contract paradigm. The bulk of the application runs off-chain, enabling real-time order submissions and cancellations while maintaining safety. For each order, the server returns a signed commitment, ensuring the integrity of the transaction. The server batches orders and creates a coprocessor job to run the batch against the state transition program to match orders. InfinityVM posts these results on-chain, guaranteeing the state of the CLOB. Verifying parties can audit the state transitions by checking the order book and commitments. If a faulty state transition is detected, it can be challenged, leading to the removal of fraudulent state transitions. This trustless and performant CLOB implementation improves upon previous designs. InfinityVM unlocks sophisticated dynamic fee AMMs that benefit from off-chain compute. This approach enables dynamic fees based on transaction volumes or account standing, which was previously impractical due to computational constraints. InfinityVM allows for real-time calculations and results, reducing latency and compute costs while maintaining the integrity of state transitions. Coprocessors bring off-chain compute on-chain, implemented with ZK or optimistic verification. Enshrined rollups, associated with the Tezos ecosystem, focus on smart contracts that maintain the state of the rollup on the base chain. InfinityVM differs by enshrining off-chain compute, allowing applications to compose off-chain compute with on-chain EVM applications, enhancing scalability and performance. Rollups with beefy sequencers use a centralized sequencer with significant resources, allowing for high transaction throughput on existing blockchain VMs. InfinityVM generalizes this idea, enabling high-performance servers to handle more load and provide better user experiences. These applications use off-chain infrastructure for scalability and flexibility. Contingent rollups are blocks dependent on the state of another domain, allowing for scalable and flexible applications. InfinityVM allows these blocks to be contingent on the same state, enabling more expressive and scalable applications without the constraints of on-chain execution. Franchise sequencers allow applications to post state commitments to the chain, enabling developers to build applications independently while inheriting blockchain benefits. InfinityVM mitigates the high costs and latency of ZK-based systems by enshrining verification within the protocol. Aggregation layers like AgLayer connect rollups via shared liquidity bridges and ZK validity proofs, enhancing cross-chain interactions. InfinityVM aggregates applications as their own servers, achieving synchronous composability across applications without relying on external shared sequencers. CarTSI enables off-chain nodes to run application logic and verify it within the CarTSI Layer 2 ecosystem, focusing on reproducible and deterministic builds. This approach is similar to InfinityVM, but follows a different method, incorporating off-chain compute into the network to run machines and verify computations. Naysayer proofs optimize ZK verification costs by allowing proposers to generate ZK validity proofs without internalizing the cost. InfinityVM takes this a step further by avoiding the need to generate ZK proofs at all, enabling lower latency and compute costs while maintaining the benefits of ZK systems. InfinityVM introduces a paradigm shift in decentralized compute by leveraging verifiable off-chain execution. This allows for scalable, flexible applications with user experiences comparable to centralized applications. InfinityVM's enshrined verification defines the canonical chain by off-chain compute, enabling fraud proofs for off-chain work. This approach unlocks new capabilities for on-chain applications, preserving blockchain security while matching centralized system efficiency. This slide lists the references used in the presentation, providing sources for further reading and validation of the discussed concepts.